Hello everyone, this is PCB, your trusted PCB partner. Today our topic is impedance calculation and practical line width control. Welcome back to the 4-layer board impedance control course. In the last lesson we learned about the rhythm and characteristics of microstrip lines and how impedance is affected by physical factors. Today we will turn this theoretical knowledge into practical application, learning how to determine line width through impedance calculation. In PCB design, we usually don't manually use complex formulas to calculate line width, but instead rely on specialized tools. PCB manufacturers generally provide their own impedance calculation tools, which is the most accurate method because their data is based on specific materials and process parameters, making it highly precise. So, if you have already carefully selected a reliable manufacturer, you can effectively communicate with them throughout the entire design phase, which then allows for the generation of very precise and accurate impedance calculations. Some high-end EDA tools also have built-in impedance calculation functions. There are also many free impedance calculation tools available online. You can input parameters such as dielectric thickness, dielectric constant, and copper thickness, and then work backwards from the target impedance to determine the required line width. Here we have an online calculation tool, this one.
As we can see, we select the type as microstrip line.
This is the method we use, and it also offers several other component options. Here are the calculation formulas along with some recommended values. You can also substitute your own values into these formulas. There are also two modes available. The first is to calculate the line width, and the second is to calculate the impedance. In most cases, we use it to calculate the line width when the target impedance is known. I've set a group of reference values. Target impedance is 50 ohms, copper thickness is 35 micrometers, dielectric thickness is 0.15, and for the dielectric constant, we use the common value of 4.2 for FR4. The calculated result is 9.576, so when drawing the trace, you can set it to this value or set it to 10 mils. Both are acceptable, though there will be some slight deviation. Now, going back to our PCB, we can see that this PCB is labeled with impedance information. These two layers, this one is marked 33113, and this one is also marked 33113. This 33113 actually refers to these two dielectric layers, the value of the dielectric between the top layer and the dielectric interface, and between the bottom layer and the power plane. So, what does 33113 mean? The dielectric constant is 14,111, which is also helpful for us in the future. If we are unsure about the factory, we can specify this value when handing over to the factory and have them manufacture according to the requirements. This is also a very good approach. Now that we thoroughly understand how to accurately calculate it, when we are carefully routing our traces, we can precisely draw the trace width according to the meticulously calculated value to effectively control its impedance and thus successfully avoid common pitfalls and significant issues that frequently affect impedance control and overall signal integrity. The first point is to avoid making slots or splits in the reference plane. Any split or cutout in the reference plane beneath a signal trace will interrupt the signal return path, causing impedance discontinuity and resulting in reflection. This is a common mistake. Here, I specifically made an example. At this spot, I made a cutout in the reference plane near the motor. For these four traces, their impedance becomes discontinuous and reflections will occur at the edges. So this situation must be avoided. Next, avoid having high-speed traces cross over different zones. Never let high-speed signal traces cross over voids in the power or ground planes because this will completely lose the reference plane, resulting in severe impedance mismatches and EMI issues. This is even more serious. For example, if I use this line as a boundary on this layer, I use ground on the left side of the stack up and cover a section of power on the right side. This is strictly prohibited. It will cause a complete imbalance in impedance, so this must also be strictly avoided. Next, avoid excessive vias or discontinuities. Try to route on a single layer as much as possible and only use vias when absolutely necessary, following the principle of introducing as few vias as possible. Also, be careful not to use 90-degree angle. Although the impact of manufacturing processes is limited nowadays, theoretically, any 90-degree angle will cause slight changes in impedance. Try to use 45-degree angles or straight lines instead. From this design, you can see that all the traces requiring impedance control are straight lines. So I also recommend that you avoid even 45-degree angles whenever possible and use straight lines instead. Today we learned how to use impedance calculation tools to determine trace width, and we also emphasized the common routing mistake of creating slots in the reference plane. Impedance control is the cornerstone of high-speed PCB design, and mastering these techniques will make your designs more robust and reliable. I hope that through the content of these two video lessons, you have gained a deeper understanding of impedance control in 4-layer boards and can apply this knowledge in your actual project. If you enjoyed this video, please subscribe to my channel for more content. Thank you all.